Howdy, this is a presentation for the paper review, Methods for Assessing Proppant Coverage Along the Lateral for Plug and Perf Treatments. The paper review is available upon request. The goal of this paper is simple. The models aim to determine allocation of proppant among perforation clusters. The focus of this paper is well 6, which was equipped with a fiber optic cable for DAS and DTS measurements, as well as a permanent downhole gauge for exact calculations of pipe friction and bottom hole pressure. In addition, an ultrasonic device was utilized to measure perforation entry hole sizes and casing wear at frac plug setting depths. The following dataset was used to perform 5 categories of analysis: pipe friction pressure, step-down testing, perforation entry hole erosion, treating pressure, treatment allocation, and uniformity. The subject of this paper are the 12 wells drilled by ConocoPhillips in 2022. Here we can see a gun barrel view looking toward north from the surface pad. The completed lateral length was 8,435 feet, while the average true vertical depth was 6,842 feet. The perforation count varied from 2 per cluster and 16 per stage for frac stages 2 through 11 to 3 per cluster and 24 per stage for frac stages 12 through 29. The proppant was a high quality, well sorted 5120 mesh sand, and the fracturing fluid was slick water. Here we look at the job parameters versus time in well 6. Due to a progressive erosion of the perforation entry holes and subsequent decrease in perforation friction, all pressure tracks in this figure show a declining trend. In well 6, oriented perforations were shot at a face angle that was offset 180 degrees from the location of the fiber optic cable. There is significant uncertainty in prediction-based pipe friction pressure and bottom hole treating pressure, when accuracy in pipe friction is critical for making important determinations. Having at least a single or preferably multiple downhole gauges is indispensable. Step-down tests were conducted at the end of 12 frac stages, enabling near wellbore friction pressure to be analyzed for determining perforation and tortuosity frictional components, and the average perforation entry hole equivalent diameter. 12 step-down tests were performed in well 6. The step-down process begins with establishing a stable treating pressure at the maximum injection rate according to design or pressure limitations. Instantaneous shut-in pressure is representative of the average bottom hole fracturing pressure among intervals or clusters. The results of the derived average perforation hole sizes from step-down test analysis and ultrasonic measurements are shown in the following table for all 12 end-of-job step-down tests. Understanding can be gained from this study. Changing erosion rate can be attributed to a larger volume of proppant passing through each perforation for the 2 perforation per cluster case and a diminishing rate of erosion after a critical volume of proppant has been pumped. The coefficient of entry hole diameter variation and uniformity index are defined below. It is beneficial for the perforating system to yield an extremely low CV. Uniformity index provides a quick look at the nature of proppant distribution along the lateral. The guidance to increase the perforation count per cluster needs to be tempered with the number of perforation clusters being treated per frac stage and the recommended limit to the initial entry hole size. In calculations, using a smaller than actual hole area as a starting point will lead to a larger than actual eroded area. This can be physically observed in the experiments. Uncertainty in the initial perforation hole size also affects the reliability of treatment allocation and uniformity indexes for both erosional and DAS based models. Well, X was analyzed to provide insight into this effect. There are slight differences in treatment uniformity and proppant allocation among the compared computational models when using exact and average base entry hole sizes. A clear source of error is friction. Firstly, the pipe casing friction is noted. Pumping service vendors provide estimates of pipe friction pressure which are used in calculating bottom hole treating pressure during frac treatments. As exemplified in this figure, these friction pressure estimates and associated bottom hole treating pressure calculations are often in error. Another source of error in this paper is erosion. Secondly, the proppant-induced perforation entry hole erosion is noted. Erosion is a two-step process and it is supported by a pressure analysis-based study of limited entry treatments. The rate of BHTP decline and associated hole enlargement levels off after a certain amount of hole enlargement has taken place. In this case, after 29,000 pounds of proppant flow through per perforation. This paper provides useful insight of the methods for assessing proppant coverage along the lateral for plug and perf treatments. There is a necessity for a permanent downhole gauge to accurately calculate pipe friction pressure and near wellbore friction pressure. The step-down test can be used to check the accuracy of downhole perforation entry hole measurement systems. Comparison of DAS and erosion-based models for allocating proppant among perforation clusters showed a lack of agreement in the well 6 case study. The uniformity index metric is useful as a qualitative indicator of treatment efficiency. Having at least 3 perforations per cluster has also been observed to reduce the impact of proppant inertia. Thank you. Any questions?